D'abord, merci à tout le monde d'être ici. Je suis bien content de vous voir. Peter, can you hear me?
Yes.
Yep. So thank you for being with us also. As you already know, I'm going to present you my project on the development of flapping foil turbines with the use of elastic supports. So first of all, most of you already know, but a hydrokinetic turbine is simply the equivalent of a wind turbine, except that it extracts the kinetic energy of river or tidal currents instead of the wind. And here you can see the most traditional design, which is known as a horizontal axis turbine. However, my study deals with a slightly different concept, which involves flapping foils. And basically, a flapping foil is simply a foil that undergoes two combined motions, up and down motion called the heave motion, and a rotating motion called the pitch motion. Several studies have already considered this type of turbine. And among these works, we can think of the work of Kinsey, a former researcher in our group. And with a large-scale prototype, they successfully showed that we can extract a significant amount of energy from the flow with such devices when we prescribe the foil motion to be, well, adequate motions. So it's a bit hard to see here, sorry, but this video was taken underwater, and you can see the blade oscillating here, and there's another blade over there. And so this was successful in that sense to be able to show that we can extract a large amount of energy, but at the same time, this work highlighted the fact that in order to be able to prescribe some specific foil motions, we need some relatively complex mechanisms. So you can see there's a lot of rigid links here. The mechanisms are quite complex, and the problem with that is it results in higher costs of the device, higher risk of failure, and also to some energy losses because of the friction in all the moving components. So we needed a simplified alternative, and this is where my project comes in. So instead of trying to simply optimize the mechanical design, we decided to go for a more drastic change, and this is the use of passive motions. So what we mean by that is that we are getting rid of the rigid links that are generally used to connect and to couple both degrees of freedom in order to impose specific foil motion. So instead of using those rigid links, we simply attach the foil with elastic supports. So elastic supports are simply springs and dampers. As a result, we can no longer impose specific foil motions, and the motions will result from the interaction of the foil with the flow and those elastic supports. So they will depend on several structural parameters, such as the spring stiffnesses, the mass of the foil, its mass distribution, position of the pitch axis, etc. And therefore, the challenge in designing such a turbine resides in finding an adequate set of parameters that will result in optimal motions in terms of energy extraction. So in order to better understand what we mean by passive motions, it is useful to decompose the foil motions into 5 different parameters. First of all, we have the motion shape in heave. So for example, it could be a simple sine wave with a given amplitude. Then we also have the frequency of this motion. Same thing in pitch, motion, shape, and frequency of the pitch motion. And then finally, the phase lag between both motions. So we can either constrain or leave any of this parameter free. And depending on the different combinations, you can obtain slightly different turbine concepts. So for instance, we could decide to connect the heave motion to a slider crank mechanism, which would be attached to an electric generator. And we can use a controller to impose a constant rotational velocity for the electric generator. So if we do that, we are constraining the motion shape in heave because of the slider crank mechanism, and the frequency also because of the controller. However, if we simply use a spring to attach the foil in pitch, then the motion shape and the frequency of the pitch motion are free. They are not constrained. And the phase lag between both motions is also free. Then we can decide to remove the controller so we can no more impose a specific rotational velocity of the generator, and therefore the frequency of the heave motion is no more constrained. And if we go a step further and remove the slider crank mechanism and simply use springs and dampers also in heave, now we are not constraining anything. So all the motion parameters are free. And this is what we refer to as a fully passive flapping foil turbine. Two main metrics are used to quantify the performance of flapping foil turbines. So when the motions are periodic and the friction is neglected, we can show that the power coefficient, which is simply a normalized measure of the power that is available for an electric generator. So CP gen is for generator. So this power coefficient is simply equal to the sum of the power that is extracted by the heave motion and the power that is extracted by the pitch motion from the flow. Another important metric is the efficiency, which is simply another normalization of the power, which involves the overall displacement of the blade D. And so it is a measure of the ratio between the power that can be converted into electricity over the power that passes through the kinetic energy flux passing through the turbine swept area. So as I said, a lot of studies have already considered the fully constrained turbine. So this is a turbine for which all the 5 motion parameters are constrained. So we are imposing specific foil motion, typically sinusoidal motions. And when we prescribe adequate motion, we can obtain efficiencies of the order of 45%. And this typically occurs when we use a reduced frequency between 0.10 and 0.25, a pitch amplitude of the order of 80 degrees, a heave amplitude of 1 chord length, and a phase lag of 90 degrees. Then much fewer studies considered the use of passive motions. And among the different possibilities of constraining or leaving free all the parameter, the most popular concept making use of passive motion in the literature is this one. It's a semi-passive turbine with a prescribed pitch motion and a passive heave motion. And with that concept, efficiencies of the order of 20 to 30% have been reported. Then, even much fewer studies have considered the fully passive alternative, the fully passive concept. And also, most of these works consider the simplified version of the turbine and a very small Reynolds number of 1,000. More recently, Jean-Christophe Veilleux, who is a former master's student in our group, considered a more general version and also a more realistic Reynolds number for practical application of 500,000. And these studies showed that we could obtain an efficiency of about 30% with the fully passive turbine. So overall, what we can say from the literature is that it is possible to achieve interesting efficiencies with passive motions, but so far this increased simplicity in terms of the mechanical design has come at the cost of a smaller efficiency, because we could not match the best efficiencies of the fully constrained concept. So this brings us to the objectives of my work. So the main objective is to evaluate the power generation performance of flapping foil turbines with passive motion. More specifically, we first wanted to prove the feasibility and the potential of a real turbine prototype, a real fully passive turbine prototype, because most of the work that had been conducted on fully passive turbine were numerical works only. We also wanted to test new types of semi-passive turbine with a passive pitch motion, and I will tell you why in a few moments. Then we wanted to understand the dynamics of passive pitch motion, passive heave motion, in order to optimize the efficiency of the device. And ultimately, what we wanted is to reach the same level of efficiency that can be achieved with a fully constrained turbine, but without having to prescribe the motions. So now let's talk about the results. The thesis is composed of 4 papers, so I will present you a brief overview of their content. I won't present you everything because due to the time limitations, but yeah, I will refer you to my thesis if you want more information, or you can just ask me some questions also after the presentation. So this first paper is entitled Experimental Investigation of the Energy Extraction by a Fully Passive Flapping Foil Hydrokinetic Turbine Prototype. And so as the title says, it is about a series of experiments that we have conducted on a real fully passive turbine. We wanted to do that to prove the feasibility, to show that we could obtain interesting efficiencies experimentally, and not only with numerical simulations. So we based our design on previous numerical results from Jean-Christophe Veilleux, former student in our lab, and we tested it at the facilities of the University of Victoria. So what you see here on the left is the turbine blade, so it is the only component that was located underwater. And on the right, you see the rest of the turbine setup, which is above the free surface. And basically, well, since it's a fully passive turbine, the blade was free to move in eve and in pitch, so it was simply supported with elastic support, so springs in eve here, springs in pitch, and a damper in eve. So the next slide, I'll show you how the turbine behaves. So it is a video that you will see. Well, it's a top view of the setup. And in the video, you'll see that the water is flowing from the bottom right corner of the screen toward the top left corner. And the eve motion is in that direction. And the blade, which is here, is allowed to rotate around an axis about here. So before presenting you the video, let me just remind you that this is a fully passive device. So we are not constraining any of the motion parameters. So this means that, well, nothing guarantees that the blade will even move. It could simply stay at its equilibrium position, or it could start to undergo very irregular motions. But, well, obviously, I didn't choose this case randomly, and the title says it's a high-efficiency case. So you'll see that when we let the blade go, it quickly starts to oscillate and reaches a periodic regime of relatively large amplitude, both in eve and in pitch. So this is, again, pretty impressive because, as I said, we are not imposing anything, but we observe very, very periodic, very regular motions. So now if we look at these motions in more details, so what you see here is the eve motion over time in blue, the pitch motion in red. And again, you see that they are really periodic, very regular, and that the amplitude are quite large, about 1 chord length in eve, almost 90 degrees in pitch. And on the right, it's a zoom of one turbine cycle. So it's a zoom of the gray, the shaded area here. And you see again the eve motion in blue, pitch motion in red over one complete oscillation. And what we can notice from this figure is that the maximum pitch position is reached about a quarter cycle after the maximum eve position. So this corresponds to a phase lag of 90 degrees. And because we obtain very regular motion, large amplitude, and a phase lag of 90 degrees, which are all optimal ingredients for an optimal energy extraction, we could obtain a very interesting efficiency of 30%. So we were able to match the same level of efficiency that had been obtained numerically with a real turbine prototype, even with the presence of friction, finite span blade, and also the presence of a free surface. So this is exactly what we wanted to achieve with this prototype. So to sum up, we proved the feasibility and the potential of the concept. However, the efficiency remained smaller than what can be achieved with a fully constrained turbine because let me remind you that the maximum efficiencies with fully constrained turbine is about 45%. And now we obtain 30. And then lastly, a deeper analysis also showed us that the generation of large leading edge vortices, LEVs, were playing a crucial role in the turbine dynamics of, well, a crucial role in the dynamics of this fully passive turbine. So here you see contours of vorticity, and the big blue spot is a strong leading edge vortex that was generated during the foil oscillation. And so this is not really a problem by itself. However, we know from the literature that higher efficiencies can be achieved when no LEVs are generated. So for instance, if we look at some results from Kinsey on fully constrained turbines, we can see that some cases were characterized by large leading edge vortices, and those cases were actually limited in terms of efficiency to about 35%. On the other hand, some other cases were such, the motion of such cases, of other cases were such that LEVs could be avoided. And those cases were characterized by much higher efficiencies of about 43%. So this raises a question. How can we avoid LEVs with fully passive turbine? And if we do so, can we match the same level of efficiency? So this brings us to the second paper of the thesis, which is entitled Investigation of the Energy Extraction Regime of a Novel Semi-Passive Flapping Foil Turbine Concept with a Prescribed Eve Motion and a Passive Pitch Motion. So, as the title says, we are now considering a semi-passive turbine, so a slightly different concept. And for this specific turbine, we considered a foil for which the eve motion is prescribed to follow a specific sinusoidal motion with a given amplitude and a given frequency. But the pitch motion is free, so the foil is attached simply to a spring in pitch, and therefore the pitch motion is governed by a mass-spring equation with a special term here, which is very important, and I will tell you more about it in a few slides. So the reason to study such device is twofold. First, this semi-passive concept is interesting on its own because it is logical to connect the eve motion to an electric generator, because most of the energy extracted from the flow by flapping foil turbines is actually extracted by the eve motion. And secondly, it's also a convenient way, this concept provides a convenient way of studying the dynamics of passive pitch motion because it reduces the number of governing parameters compared to the fully passive turbine. So we tested several sets of parameters that we selected using a reverse engineering technique that is described in the thesis. I won't go through all the details of the parameters here, but let me just remind you that here we impose a specific eve motion. So the eve motion is a sine wave with a given amplitude and a given frequency, but the pitch motion is free. It is elastically supported in pitch. And so using a specific set of parameters, we obtain this pitch motion. So this pitch motion is not imposed. It results from the interaction of the flow with the supports and the foil. And again, you see that the motions are very, very regular, very periodic. The amplitude is still also quite large, 85 degrees in that case. This bottom right figure also shows you a zoom of one complete oscillation. So again, the eve motion is shown in blue, pitch motion is shown in red, and still we have a phase lag of 90 degrees. So maximum pitch position is reached a quarter cycle after the maximum eve position. So phase lag about 90 degrees. And the biggest difference with the case I showed you before for the fully passive turbine is that now we could avoid LEVs, so no leading edge vortices are generated for that specific case, even if we are not imposing the pitching motion. So because of all that, because we could avoid LEV, have a phase lag of 90 degrees, large amplitude, we were able to obtain an efficiency of 45%. So we were able to match the same level of efficiency, the maximum efficiency that can be obtained with a fully constrained turbine, but without constraining the pitch motion. So now we can ask ourselves, well, how can we avoid LEVs? So to understand that, let me remind you that the power coefficient available at the generator is simply the sum of the power extracted in heave and the power extracted in pitch. But in that specific case, the pitch motion actually does not extract energy. It provides energy to the flow. This is why we have a negative value here. And this thing, the fact that we have a negative value, is typical of cases without LEVs, without leading edge vortices. So if we go back to the results of Kinsey for a fully constrained turbine, you see that the cases that were characterized by large leading edge vortices, well, they were characterized by value of CP theta that were very close to 0. On the other hand, the cases that didn't have leading edge vortices were characterized by a much smaller values of CP theta. So this means that if we want to benefit from the higher efficiencies that are related to the cases without LEVs, we need to be able to deal with negative values of CP theta. And so how can we do that? Well, if we have a negative value here, it means that we need another source of energy to sustain the pitch motion. And this other source of energy is actually the eve motion itself. So what happens is that the eve motion extracts energy from the flow. A fraction of it is transferred to the pitch motion to sustain it, and the remaining fraction is available to be converted into electricity. Now we can, how can we transfer this energy from the eve motion to the pitch motion? Well, it is via this inertial coupling term, the term with the parameter S which is called the static moment. And this parameter actually is simply the product of the mass undergoing the pitching motion m theta and x theta, the distance between the pitch axis and the center of mass. So it is non-zero when the pitch axis does not coincide with the center of mass. So in order to understand its effect, I can show you a very simple demonstration. So if I take this rod and I hold it by its center of mass, which is at the center of the rod, and I start to oscillate it, to move it up and down, well, there is no tendency for the rod to pitch. However, if I hold it at any other location than its center of mass, and I start to move it up and down, well, you see that there's a natural tendency for the rod to start to pitch, and this is because of this exact inertial coupling term. There is a transfer of energy from the heave motion to the pitch motion. And then the last thing that we need to know is that if we want the transfer of energy in the right direction, so from the heave motion to the pitch motion, we can show that we need a positive value of the static moment. And in practice, it means that the center of mass must be located downstream of the pitch axis. So by doing that, by placing the center of mass downstream of the pitch axis, we were able to avoid LEVs, and doing that to obtain efficiencies that compete with the best efficiencies that were previously observed with fully constrained turbines. So now the next question is, because we obtained this for a specific set of parameters, but can we also generalize these results to several sets of parameters? And so this is addressed in the third paper. Yeah, well, I won't read the title because it's quite long, but yeah, basically this paper is the follow-up of the previous paper. It's also on a semi-passive turbine, the same semi-passive turbine concept, but we investigate the effect of some structural parameters that were not investigated in the previous papers. So for example, here we investigate the effect of the pitch stiffness coefficient and the moment of inertia. So this first figure shows you the efficiency as a function of the pitch stiffness coefficient for a given value of the moment of inertia. And what you see is that the efficiency is very sensitive to the pitch stiffness coefficient. Actually, it drops from its maximum value to 0 with an increase of about only 10% of the pitch stiffness coefficient. Also, we can, well, if we vary the value of the moment of inertia, shown by the different colors, you'll notice that the maximum efficiency is reached at different values of the pitch stiffness coefficient for different values of the moment of inertia. So this suggests that the dynamics of this turbine, the pitch dynamics, and therefore the efficiency, depends on two different parameters, the moment of inertia and the pitch stiffness. However, we can take into account the fact that the pitch motion is very close to a sine wave, and therefore the pitch acceleration and the pitch motion can both be approximated by sine waves. And using this fact, we can approximate the inertial term and the stiffness term that appear in the pitch equation of motion. So we can combine them and approximate them with a single term, which involves a new parameter that we call the effective inertial stiffness parameter, lambda theta. So this effective parameter combines the pitch stiffness coefficient, the frequency of the motion, and the moment of inertia. So now if we take this same data, but we plot it against this effective parameter instead of the pitch stiffness coefficient, well, you see that all the three curves collapse into a single curve. And what this means is that the heave dynamics do not depend on two separate parameters, but rather on one single effective parameter, which is the effective inertial stiffness parameter. So this has some useful consequences in practice, because it says that the pitch dynamics is essentially insensitive to the moment of inertia and the pitch stiffness coefficient, as long as we keep this, well, lambda theta, this effective parameter constant. And this is shown in the two right figures here. So you see the efficiency in black, the pitch amplitude in red, and the phase lag in blue, well, as functions of the moment of inertia and the pitch stiffness coefficient. And so you see that they remain pretty much constant over large variations, so from 0 to about 10 for the moment of inertia and the pitch stiffness coefficient. So this is very useful in practice because it gives some, well, freedom for the designer of such turbines to obtain large efficiencies for different structural parameters. So we were able to combine the moment of inertia and the pitch stiffness into one single effective parameter, and doing that, we could maintain and generalize the results, so we could maintain high efficiencies over large variations of the structural parameters. And so the next and last question is, can we also apply all these findings to the fully passive concept? So in the fourth paper, actually, what we do is to revisit the fully passive concept using all the knowledge that we have gained by studying the semi-passive turbine. So we did that, and we were able to obtain, well, sinusoidal motion in Eve and in pitch. And then by placing the center of mass, again, downstream of the pitch axis, we were able to avoid leading edge vortices, as you can see here. And doing that, we obtained an efficiency of 53.8%. So this is very impressive because it's even higher than the maximum efficiency that had previously been obtained with fully constrained turbines. So it exceeded actually the initial objective that we had. Then we can also derive some effective inertial stiffness parameters in Eve. So first, I'm showing you here the efficiency as a function of the Eve stiffness coefficient, and for different values of the Eving mass. So the different colors are different values of the Eving mass. And again, you see that the maximum efficiency is obtained at different values of the Eve stiffness for different values of the Eving mass. However, the Eve motion is also close to a sine wave in that case for the optimal cases. And so we can use exactly the same procedure to derive another effective inertial stiffness parameter, lambda h, which involves the Eve stiffness coefficient, frequency of the Eve motion, and the Eving mass. And so, yeah. And so if we do that, you see that this data can also collapse into, well, roughly one curve. And so it says, again, that the Eve dynamic is, well, dependent on one single parameter, one single effective parameter, rather than two separate parameters. Then in pitch, it's a bit different now, because unlike what we had for the semi-passive turbine, the frequency of the foil motion, F, is almost directly proportional to the pitch natural frequency for the fully passive turbine. With the semi-passive turbine I presented you earlier, things were different because we were imposing a frequency in Eve. We were imposing a specific foil motion in Eve, and the frequency of the pitch motion was synchronizing itself to the Eve motion. So actually, the frequency was not dependent on the moment of inertia and the pitch stiffness coefficient. But now for the fully passive turbine, we are not imposing any frequency. So the frequency, as we see, depends on the pitch natural frequency, and therefore depends also on the moment of inertia and the pitch stiffness coefficient. And so we can show that because of that, the parameter lambda theta that we derived earlier is always equal to 0. So it becomes irrelevant to characterize the dynamics of the fully passive turbine. And so it is more useful. It's just not only more useful, but it's just that the dynamics of the pitch motion for the fully passive turbine is rather characterized by the pitch natural frequency. So if we plot the efficiency as a function of the pitch natural frequency, we again observe, well, roughly one single curve. So it means that the dynamics of the pitch motion for the fully passive turbine depend on this specific parameter, the pitch natural frequency, and not the effective inertial stiffness that we derived before. So to conclude, the efficiency, we showed that we could exceed the maximum reported efficiency that we had for a fully constrained turbine. The Eve dynamics is characterized by an inertial stiffness parameter, lambda h, but in pitch it's different because the frequency is correlated to the pitch natural frequency. And because of that, this parameter, the pitch natural frequency, becomes more relevant to characterize the pitch dynamics of the turbine. So to conclude, let's go back to the initial objectives of this work. So we successfully proved the feasibility and the potential of the fully passive turbine experimentally because we could obtain a very interesting efficiency with our experimental setup. Then by studying the semi-passive turbine, we showed how to avoid LEVs, and we also showed that by doing that, we can optimize the efficiency. After that, we showed that we can derive some effective parameter that allow us to vary the structural parameters and still maintain large efficiencies. And then we use all this knowledge to optimize the fully passive turbine and reach an efficiency of 53.8% with the fully passive turbine. Finally, there is still a lot of work that remains to be done on flapping floor turbine with passive motions. For example, before those concepts can be brought to a commercial stage, we need to investigate in more details some real-life effects, as I call them. So, for example, the 3D effects, blockage effects, also the effects of having some perturbations, either in space or in time, in the upstream flow. And actually, this has already been initiated by our colleagues at the University of Victoria with the master thesis of Dylan Iverson. So they used the exact same prototype that we used in our work to start this kind of analysis. Then there are several alternative concepts making use of passive motions that have not been considered so far. And that could be interesting in some situations. So for example, if the concept that I propose in my thesis appear to be very sensitive to the perturbation in the incoming flow, while some alternative concepts could be better in certain situations. And finally, the development of flapping floor turbines will continue to benefit from more fundamental studies on dynamic stall, unsteady separation, and the generation of leading-edge vortices. So thank you very much, and I'll be pleased to answer all your questions.